Good morning or good afternoon, ladies and gentlemen. My name is IFMI, and it is a great honor and pleasure for me to give you a presentation about the characterization and calibration of optical surface topography measuring instruments. Just to give you an impression of who is talking to you now, I included a small CV. I studied physics. I was employed by the Dutch National Laboratory. I taught at the Eindhoven University of Technology in the Netherlands. I was director of Mitotoyo Research Center Europe in Best in the Netherlands. And since 2017, I have the honor of being a professor of dimensional metrology at the Catholic University in Leuven, and Leuven is in Belgium. Just to clarify where I am speaking from, this is the location of Belgium, and more specific Leuven in Europe. Leuven is an old university town. It is located near Brussels in Belgium. It has about 100,000 inhabitants. It is an old respected university. It is founded in 1425. It has about 60,000 students and 2,000 professors. Just for your interest, having a rich history, Leuven has also some famous scholars. One of them is Desiderius Erasmus, and I want to quote, just for your interest, have a quote from him for you. He made it 500 years ago again, and I will read it for you now. The English despise the French for no other reasons than because they are French. They hate the Scotch because they are Scotch. The German is at odds with the Frenchman, and both are fighting the Spaniard. What could be worse than people who fight each other only because they are named differently? There are so many things that should bring them together. Why aren't they not being sympathetic to their fellow human being that are people as well? So he was a strong opposing about narrow-minded nationalism. He was already so around 1500, and we are still waiting for some progress in humanity. Okay, up to the topic of today. I will talk about optical surface topography measuring instruments. Maybe you have some in your laboratory, maybe you see some results with it. They are fast instruments, they can measure quite fast. They are rather popular. They have a microscopic range of up to a few millimeters down to 100 times 100 micrometer. Some can expand their range doing some stitching. And these instruments, they look a bit the same at the outside. You see a microscope, objective, there is a table where you can put your specimen. This has about the same structure. Also here you can have a table, some microscopic-like structure here. And you would say maybe they are all the same, they operate the same, they all claim to do good measurements, but in fact, they are very different at the inside. There are different principles, there are different various advantages and disadvantages at all of these instruments. And the ISO community has taken some measures. They tried to tackle the difference between the instruments. What the instruments have like human beings, I would say, they have many things in common. A common way of operation that is that inside the instrument an image stack is created, and then the Z height for every XY location is found. So here is a typical structure. We have here the camera on which the image is projected. Here's the light source. Here we have an interference objective. You can also have normal objectives. Depends on the types. There's a tube lens, and then the object is imaged on the camera. and the camera takes a stack of images. So it takes images at different height. And if you look at a single pixel here, then something happens. And what happens depends on the measuring principle. Here is what happens if you have a coherence scanning instrument operating on white light. Then here is the white light interference. It happens at a certain height, and for every pixel this happens at a different height. From these heights, then for every x, y coordinate is an optimum height is computed, and then you get those 2.5D topographies where you find a z coordinate for a grid of x, y coordinates. And in the end, what is important, there is a flatness reference that can be inside the objective, or it can be the focal plane. The z value is taken from the scan along an z-axis. Here in this interference pattern, a z location is derived, and as you can see here, in the end, a nice 2.5D topography is calculated with a z height and an x scale and an y scale. And we all hope and wish this was uniquely defined and was completely free of errors, which in the end it is not, of course, unfortunately. Then what is the issues with optical surface topography, with these measuring instruments? Well, of course, all instruments claim to measure the true topography as it really is. And instrument makers have different way of specifications. And if we have comparisons to which I participated, I also organized ones, then you often see that compared to the claims the instrument makers make, the results are quite disappointing. The uncertainties quoted are much larger than you would expect from the specifications, and even then the results may be inconsistent. Here you see an example of some exaggerated specification of manufacturers, and that is in sharp contradiction to the scatter of results you find if you compare different instruments. Here is a result of an intercomparison where just a simple sinusoidal grid was sent around. It was every instrument was asked, please give us the SA in nanometers from a defined area, and even then quite a simple surface, quite limited region, everything defined, and even then we found results with different uncertainties and quite limited consistency. So it was quite disappointing, and this is illustrated here with some impression of the same surface measured in 3 different ways, with interference method, with the confocal method, and with focus variation. And we see some even between the confocal and the interference, we see some difference. With the focus variations, we see some other differences, and then the important question, which one is true in the sense that these points represent the real surface. In the ISO committee, work group 16 of technical committee 213, they are about the aerial and profile surface texture. I am involved with this. Initially, for every different instrument type, there was made a different standards, how to define things, how it should work. So we had the contact stylus, we had the confocal chromatic probe, the phase shifting interferometer, coherence scanning, the point autofocus probe, the focus variation, and confocal. They all used to have their own standard, and they still have, and then it was recognized, well, in fact, these instruments have a common ground, should do the same thing, and in fact all these standards were combined in one standard called the 600. It's ISO 25178 and then .600. It's called Meteorological Characteristics for Aerial Topographic Measuring Methods. And in parallel thereof is now developed a standard called 700, and there is the calibration, adjustment and verification of these aerial topography measuring instruments described based on these meteorological characteristics. These meteorological characteristics are summarized in a infamous table 1 of the 600 standards, and there it is assumed, and that is open for some kind of discussion, but we have fixed now in the standard. These are the characteristics which define the operation, so that are the amplification coefficients in 3 directions, the linearity deviation along 3 axes, the flatness deviation of the reference you have, the measurement noise, which defines what is the finest structure you can measure, the topographic spatial resolution, which is the finest lateral resolution you can measure, the XY mapping, which is the kind of distortion in the XY plane, and the topographic fidelity is in fact everything we do not understand that is still going wrong, even if these all are okay. If you calibrate an instrument along these points, you can do something with the results. In the first and the first aspect is that you may test the instrument specification. And also you can maybe with these results correct or improve a measurement. And once you have these results and the uncertainty in the results, you may also obtain a better uncertainty estimation for a characteristic. A characteristic may be the RA value of your surface, or a step height, or a depth of a trench you have in your surface. All these kind of things you would like to be able to measure, but also would like to be able to put an uncertainty to. I will try to explain the idea of the meteorological characteristics here. The idea is that these are common to all measuring instruments, and what is instrument specific is in fact in the background. It depends on the operation, the physical reality of those instruments, how they are operating. So in the background are always the influencing factors. It may be a reference plane, it may be the vibration of an instrument, and that will contribute to meteorological characteristics. The meteorological characteristics are the same for all instruments. Here I mentioned some, and a small illustration of the linearity and the flatness and the noise and spatial resolution, and there are a few more. They all affect the measured topography. And once you know how these affect the measured topography, you can calculate a parameter value, but also you may estimate the uncertainty in this parameter value. That is the background of the idea. Then I will go along a few of these amplification coefficients and describe some methods how to obtain these. Just for illustration, there are default methods, but that doesn't mean these are the law. You can also think of also a different method. Amplification coefficient around the z-axis. The default method is to check the z-axis using a step, a depth, measuring a step standard or a depth standard, and then the groove depth is defined as the mean distance from the line between A and B, and then the mean distance of this. It is properly defined. It was already defined for 2D in ISO 5436. It is similarly defined also in the next standard, in the 600. Then this is extended to some areas you have to measure and to have to compare. Then one thing I want to point out, that even if you measure the amplification coefficient in such a way, then if your groove is nominally this way, and you have some flatness deviation also, then the measured groove may be a bit different because you have this flatness deviation for whatever reason. If you do then the depth evaluation as it should be, for example, here we have depths of 3 nanometers, but if we have this flatness deviation, we will still have a deviation 3.4 nanometers, so 10% difference. What can we do about this? Well, I will tell you a small trick in the next slide. What you can do is shift. Here is your image of the depths of your depth standard. You can just shift along the length of the depth and then subtract these two measurements. If you subtract these two measurements, you more or less eliminate here the flatness deviation, and you get a profile A minus B, and that gives you directly exact, more or less compensated for this flatness deviation, gives you the correct value. This is an illustration of a 28 nanometer groove depth. This is the normal measurements. This is the shifted measurements, where the groove depth is just shifted over its own width. And if you then take the difference and then take the average depth of this groove and divide by 2, then you have a bias-free estimate of your groove depth. The next deviation I want to discuss with you is the linearity deviation. Your z-axis will not be perfect, even if it is perfectly calibrated. Between the calibrated points there can be some linearity deviation. The standard says you should measure several grooves, and then in fact the difficulty with this, then in fact you need a lot of steps. This is an example for a kind of steps you can use. This is a Mitutoyo miniature step gauge steps. Here you see the different step heights. They are 500, 100, 50 and 20 micrometers. From there you can derive this curve. So you can derive the actual response curve, and then you can maybe correct for the amplification coefficient, and what is remained is your deviation from linearity. This is quite complicated to do. I think there is a more convenient way which can sometimes be employed. It's a bit an underestimated alternative, and the alternative consists of measuring an inclined optical flat. In fact, this method is already described for the calibration of stylus instruments. So this is the principle. You have here an optical flat, you make a tilt, and then you, in fact, you measure if this line is still straight. If this line is still straight, then you can assume that also the linearity is perfect. However, you still do not know exactly if this optical flat is really flat, and there are some tricks to eliminate also the optical flat. So if you use a reversal method, so you measure it this way and you reverse the direction in the other way, then you have measurements A and B, and you can do some further reversal by also rotating this optical flat 180 degrees. You do that also here again, then you have a second set of measurements. And if you then take the average of all these measurements, you reverse, you flip, and you average, then you have your flat eliminated. You have also the reference of your own flatness reference eliminated. You have reduced your X-linearity correlation, and also you have reduced your noise. And here you can see typical results. The height goes from 0 to 80 micrometer, and the linearity is of this instrument used to be 0.2 micrometer, which is a very good result, in fact. Then something about the flatness deviation. The flatness deviation, it was used to be called the residual flatness. So in fact this is the flatness which remains if you measure an hypothetically ideal flat surface. The method which is agreed is that you measure a nominally flat surface, and that you can reduce the influence of the reference surface by averaging randomly chosen areas. So if this is your calibrated reference surface, which can have a quite considerable size, then here are your measured areas, and it is the best idea to take these independent. But what happens then with the it is assumed that then the effect of your calibrated reference surface is completely eliminated. But we can look to this a bit more in detail. What happens if we consider form deviations? We can consider the form being built up of orthogonal polynomials. For round surface, these can be the Zernike polynomials. For square surfaces, they can be Legendre polynomials. And now, if we look, if really putting your reference, your measurement randomly over this surface, if then really everything is eliminated, that is not completely true. The bias and tilt are automatically removed because you remove them from your measurement. The twist is not removed. This is the twist, the topography of the twist. Red is high and blue is low, as you understand. This decreases linear with the area. So if you take a smaller area, this twist is removed. And the sphericity and the cylindricity, these are also not removed, but these decrease quadratically with the area. Now, what happens? For example, consider it a 25 millimeter diameter reference specimen. If you measure 2 times 3 millimeter area, then the maximum sphericity can be 1.5 nanometer. The maximum twist can be 10 nanometer. If you want to, so this is potentially still present in your measurement. If you want to eliminate this further, is what you can do is rotate your reference surface, indicated here by green, rotate it 90 degrees and measure these areas, another set of random areas. Then you are sure that at least the twist is eliminated by reversal. Here is an example of the result of the method. So here an average image of several areas of a flat surface are eliminated. Here the area was 400 times 400 micrometer, and you can see this is the residual reference surface. It is in fact, as this was a Linux interference microscope, this is most likely the surface of the reference surface, the flatness of the reference surface, and you can see it is on 40 nanometers, quite a low value. These are some examples of flatness deviations, what you can find of different instruments. It is not, I must say, it really depends on the measuring principle, if the flat is automatically corrected or not inside the instruments. But this is what we typically find of confocal instruments. This is what we typically found of a coherence scanning interferometer, so a white light interferometer. This is what we found in a focus variation instrument, and you see they can be quite different. This is for an aligned flat, and I must say, if you tilt the flat, then you get, in fact, the correlation with some other metrological characteristics. So it's very important that the flat you use here is well aligned. If you do not align it, you have some variation even here for the CSI measurement, and here things become completely different. So here's the lesson. Yeah, if you do this, you must well align the flat. Then some more words about the measurement noise. Noise is can be considered as static and dynamic noise. We here consider the dynamic noise. So what is the noise which is added from the instrument to the measurement value? The measurement noise determines the smallest height that can be measured. And this is determined by measuring, the default method is that you determine it by measuring an optical flat repeatedly. And if you then subtract the mean measurements, you eliminate the optical flat topography completely. Default method is that you take 2 measurements, but you can also take more measurements, then you get a more stable value. So here is the idea: you do a number of measurements just of one section of an optical flat. Then you take the mean value and you subtract the mean of all these measurements, and then you take from all these measurements the mean square, the RMS value, and that is called the measurement noise. That's a characteristic for the measurement noise. If you don't have much time or you want to keep it simple, you just take 2 of these measurements and you subtract them. That is exactly the same method, just reduced for 2 measurements. There is some confusion in the literature. People think these are 2 methods. No, it is one method. Just for NS2 it becomes a bit more simple. This is an example for 2 measurements. In fact, if you do 2 measurements, you can in fact do a kind of reversal method. If you have here the 2 measurements which are taken, which both have their own SQ value, so their own noise value. If you subtract them and divide by the square root of, then you have the SQ of the noise, which is in this case 0.01. But you can also use this measurement to get an impression of the flatness. Then you take the mean value. The mean value of the flatness is in this case a bit more, 0.014. So you can do some kind of reversal method in which you separate, in which you have 2 measurements and you get 2 characteristics in once. These are some typical results from measurement noise. And measurement noise, the bad thing about this is if you take a flat surface, you get the best value for the instrument. Some instruments require a little bit of roughness, but they are not necessarily characteristics for what the noise is if you do a real measurement. Because if you do a real measurement of a rough surface and you repeat that in the same way, then you can see here the noise in this rough surface, if it is repeatedly measured, is considerably higher than the noise just taken from a flat surface. So some care has to be taken. If you really want to do an in-depth measurement for a specific specimen, you have to repeat the measurement for that same specimen. Then with the measurement noise, there are several parameters going around. One popular parameter is the so-called RMS repeatability, which is quoted by some manufacturers. This gives very low numbers, but the numbers are quite meaningless and have little relation with the true measured noise, as I just explained it to you. We did an investigation about it. We took the several parameters, we took several instruments, and here you see a scatter plot of all the difference we found. This is the real measurement noise as it is defined here. This is the so-called RMS repeatability for this same specimen, and you can see it scatters all over the place, and all the time this RMS has a very low, unrealistically low number. So this is a kind of warning: do not use this parameter as something useful. Then a characteristic is the topographic spatial resolution that is related to the smallest thing you can see in the XY direction in a microscope. What is the smallest thing you can see? And it is related to the lateral resolution, but it is not the same, because it is also the lateral resolution for which you can see some heights. And for this is so dependent on the measuring methods, is so dependent on the specimen you are using, that within ISO we could not define a default method. There are no general rules for this. Still, there are several test specimens available for which you can get an impression. We have the so-called Siemens star. We have a chirp standards with a kind of sinusoid. Also, you can measure very fine grid. See what grid you can define. And for very small heights in the Rayleigh limit, the Kirchhoff limit, in fact, for very small heights, you can do some approximation and you can really predict how much a sine, a hypothetical sine wave, will be amplified as a function of the spatial frequency, and this will be dependent on especially the numerical aperture of the objective, which also specified the Rayleigh and the Sparrow limit. So for very small surfaces, sub-wavelengths, you can do some approximation. For large wavelengths, the situation is quite cumbersome, not yet clear. Okay, then we also have the X-Y mapping deviations. These are the remaining distortion in the XY coordinates. So this is an idea. This is the ideal situation, and the XY, they may still be both linear, but there can be some image distortion, and the standard defines some way of quantifying this. Of course, this is only relevant if what you measure, for what you measure also the XY is relevant. So if you only want to measure some RMS roughness, some RQ or SQ value or RA, then the XY coordinates are often of minor importance. But there are some tricks available if you, for example, want to know if the XY coordinates which you are measuring are really square to each other, if the two axes are square. You can measure this looking at a grid. If you look here at the coordinates of the grid, and this is the coordinates of your measuring microscope, then you can rotate the grid in 4 ways, and if you then rotate back the measurements you have done, you can estimate the squareness of the measured grid and both the squareness of your measuring instruments. Mostly it is square within one degree, and mostly better squareness is not really relevant for your measurements. But just in case, there are methods to calibrate it, even if your grid itself is not calibrated for this. Other methods also exist based on a kind of triangulation. If you have a grid and you are sure in this line your measurement is well calibrated, then you can rotate the grid and measure all the mutual distances along this line, and also you can rotate the grid 45, then you have all these knots, and if you then put all measurements together with the least squares approximation, you can have your absolute coordinates, then you have your grid XY values, and if you then measure your XY values and you measure the difference for your measuring instruments, then you can have the so-called XY mapping, and you can see what is the deviation of all your instruments in such a way. It's a lot of work, but it still can be done. Then the most tricky, in fact, where the ISO committee put all the remaining problems in without really solving them. Because basically problems with a measuring instrument you cannot solve by just defining them away in a standard. So also this is not claimed here, but there are some methods to have at least an idea of how, apart from all these deviations, there still may be deviations, and all these we put together, define them as the topography fidelity. Some examples are, well, I must say, the topography fidelity is anything other than the other metrological characteristics that causes a systematic deviation of the measured topography from the real mechanical surface. So these can be missing points, spikes in your measurements. In fact, these are the two big taboo subjects in optical surface metrology. In fact, it is not well defined what to do with missing point, or what to do with spikes. Also, you can measure a different topography than you think you are measuring because of aberrations inside the optical system. And of course, if the surface is reflecting and it has an angle, then if this is the objective and this is the light coming out, and then the sensor waits for the light coming back, but in fact the light is here reflected away, so it is difficult to get a measurement value over here. What can be done is at least comparing different measuring methods. So this is the comparison, for example. You see in red and green, it's not so clear, but the red is the CSI measurements, so the interferometric measurements. The stylus, the green, is the stylus measurement, and you see they are not so bad. They are a bit okay. Here the stylus has a bit more noise. Here suddenly the stylus has a different height. How does this come? Nobody knows. Maybe a sudden aberration of the stylus. Could be, but it can also be that the stylus, that the CSI is wrong here. So this is in fact a major problem in the surface topography measurements. You have to play some tricks, and I will tell you one trick which has worked more or less for interferometric measurements. It is known in CSI, in white light interferometry and interferometric measurements, there can be some chromatic aberration effects which make tilted surfaces have a little bit different tilt than it seems to be. If there will be a path difference inside the objective, and that gives a shift of the coherence peak, and the shift depending on the location within the measuring area and also on the local gradient. What can we do about it? Well, we can get an impression by reversing the objective, so rotating the objective in its holder. Then this effect will reverse, and then we can measure the same object, but we can also rotate the object 180 degrees. Then we have again the similar situation, and then we can see what has happened to the real surface. So if we have here the normal surface as it is measured, and here we take the example of a microlens arrow measured by interferometry, we have here the normal situation. Here we have the object rotated 180 degrees, and also the objective rotated 180 degrees. Then we rotate the image 180 degrees, and we look at the difference between these two images. Also, we say, okay, the image has reversed, so we take A plus the rotated B, and we say, okay, this is the corrected surface, which I'm not completely sure if you can do this, but maybe this is true. But at least you can have an impression of the error, because if you subtract A minus the rotation of B, it should be 0, but as you can see here, what you see depends a bit on the angle, whether the angle is positive or negative, and it is in the order of 0.05 micrometers, so it is significant when you compare it to the resolution, which is in the nanometer range. So this is an example of a method which maybe gives a clue to have some indication of the topographic fidelity. So the conclusions is that the ISO series gives a framework for characterizing and calibrating optical surface topography measurements instruments. What can you do with this? Well, as I said in the beginning, you can test instrument specifications, you can correct, improve measurements, and you can obtain, with some effort, a better uncertainty evaluation for characteristics. But for doing this properly and doing this in a more standardized way, It should be good if we could make the instrument manufacturer use these characteristics for the specification. Then you know what to expect from a measurement. You know what you can do and what you can test, and also use these for making uncertainty evaluation. To make this common practice when performing measurements, this is a huge task because some of the elements are depending on the specimen you are using. So it could be advisable that some instrument maker makes standard software, but that is a bit tricky because every instrument maker wants to be his measurement perfect and is reluctant to say that it has some uncertainty, but it would be a good thing to do. So this was my story. I hope I entertained you, and I want to thank you for your kind attention.